The third way to do this problem would be to use that green Gaussian surface, this green Gaussian surface here, and look at the electric field based on that Gaussian surface. So I would use green normally to do this so that my work matched up with the color of the Gaussian surface, but green doesn't always show up so well. So I'm going to do the work for this Gaussian surface in purple. Okay, and again I'm going to start with the same exact expression, that the net flux is equal to the integral of E dot dA, which is equal to charge enclosed by my Gaussian surface over E0. Alright, when I'm looking at that E dot dA piece, I still want to break up my surface into a whole bunch of little chunks. So I'm going to break this up into E dot dA for the top, just like I've done before. E dot dA for the bottom. E dot dA for the sides. And that equals charge enclosed over E0. Okay, and again, I'll look at the dot product and figure out which things actually have flux through them. The sides have nothing based on the dot product. And then the same arguments we made before. I chose this Gaussian surface because E is parallel to dA at each point, because E is constant, so I can pull that E out of the integral, and because area is easy to calculate. So this quickly jumps to E times area of the top, where that's the top of my Gaussian surface, plus E times area for the bottom, where that's the bottom of my Gaussian surface, and these two areas are the same size, is equal to charge enclosed over E0. Okay, how much charge do I have enclosed? Again, I'm going to set up that same proportion. My proportion is going to be identical to this one with a tiny exception. So total charge is Q. Total area that has charge on it, I'm going to call 2A. Because again, I define this area as A. Well, I have A and another A, so that's 2 A's. And then equals charge enclosed. And now, how much area is enclosed that has charge on it? Well, before I called this area enclosed. That's what I called A enclosed there. Well, now I have this area, but I also have another section of that same area. So I'm going to call that 2A enclosed. Okay? Some things cancel out, like these 2's right here. And so I have total charge over total area times area enclosed gives me charge enclosed. I'm going to plug that back in here and say that this area for the top and this area for the bottom are the same areas. So 2 times E times A is equal to charge enclosed, which is Q total area over area enclosed, where the area that's enclosed that has charge on it is just one of these sides. This length, this portion of the charge enclosed, has the same area as this does, so this A and this A are the same thing, divided by E0. Okay, and then some things cancel. These A's cancel, and I'm left with, for the third time, the expression that the electric field is equal to Q over 2A E0, which is the same thing as sigma over 2E0. So no matter what I'm doing with this, I should, and I do, get the same electric field, whether it's an insulator or a conductor. Again, your book does some confusing things. Various textbooks talk about this in different ways. I think this forces you to think about Gaussian surfaces and flux in a really good way, which is why I took the time to do it. And I like this proportion piece because it helps you think about it, and it eliminates the fringing of a field. So hopefully these 3 videos help.